Algebra 2, Lesson 33, Applying the Counting Principles. So a lot of what we're covering is Algebra 1 material in terms of what we're going to cover in independent and dependent outcomes. So in counting theory, an experiment is any process that results in one or more outcomes. So an experiment could be flipping a coin, getting heads or tails, right? Each of those is a different outcome. Rolling a dice, spinning a spinner, putting your hand in a bag and pulling out a colored marble, taking a deck of cards and picking a card out of the deck. All of those are experiments with outcomes, okay? If a process is repeated one or more times, each time it's performed is called a trial. We're testing it. Okay, and the experiment consists of all of the trials. So if I have a deck of cards and I'm handing out multiple cards to multiple people, right, or one card to each person, the whole of what it is that we're trying to do is considered the trial. Okay, all of the individual outcomes, right, are parts of that experiment. Okay. All right, so, but an experiment consists of all the trials. So each one of you picking a card would be a trial. Right? All of the trials together constitutes the experiment. The sample space for an experiment is the set of all possible outcomes. Okay? So that's the sample space. It's any possible outcome. For instance, if I'm flipping a coin, how many outcomes do I have? Two. I have two possible outcomes. So that's my sample space, heads or tails. Now, every time I flip that coin, the possible outcomes begin, if I say, I'm going to flip a coin 6 times or 4 times, let's say I'm going to flip a coin 4 times, what are all the possible outcomes? Well, that number begins to get bigger and bigger because I could get heads, 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 heads. I could get heads, 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 tails. I could get heads, heads, tails, heads. You see how, right, we have all these different possibilities that start to happen. The more times I flip that coin, the more possibilities there are for that sample space. Does that make sense? Okay. So a sample space for an experiment is the set of all possible outcomes. So we would use a tree diagram, which you see in your book, for example, number 1, to show a sample space. All right. So every time I try it again, I'm getting an option for heads or tails. Okay. If I'm talking about flipping a coin, right, that changes based upon what it is that we're doing. If I'm talking about a deck of cards, that's different than flipping a coin. If I'm talking about rolling a dice, a fair die has 6 sides, right? So every time I roll a die, right, I have a 1 in 6 chance of a particular number, right? I have a 50-50 chance of an even or an odd, right? And then I can increase that even more so if I'm rolling more than one die, or if I'm rolling the same die more than one time. So those are the different types of outcomes that we could look at that are going to change probability, that are going to change odds, that are going to change all these sample spaces. So an event is any subset of a sample space. So an event is any outcome or set of outcomes. If you need only to count outcomes rather than actually show them, one method that can sometimes be used is to apply the addition counting principle. Okay, and we're going to see that here in a second. Okay, right now, actually. So suppose a trial can result in any one, let's say, in one outcomes. That just means it could be 10, it could be 12, it could be 1, it could be 2. We're just using in as a variable for the number of outcomes it could be. Outcomes from category in 1, in 2, outcomes from another category, and so on. If there are k different outcomes, then the total number of outcomes would be the number of outcomes from the first time, the number of outcomes from the second time, number of outcomes from the third time, all the way up to k, right? We would just add the outcomes all up together, okay? Now, it's why we call it the addition counting principle, because I'm just adding up outcomes, okay? So flipping a coin has 2 possible outcomes, right? So if I flip it once, I got a 50-50 chance of something happening. Flipping it again, that's 1/2 plus 1/2 plus 1/2, however many times I'm doing it. Begin to understand that? Okay? All right. So 2 events in a sample space are mutually exclusive if they have no outcomes in common. For instance, if I was going to flip a coin and then spin a spinner, right? What happens in those 2 sample spaces is completely different, right? over here I have heads or tails. Over here, if the spinner has 5 spots, I'm getting a 1, 2, 3, or 5, right? Those two things are mutually exclusive. What happens when I flip that coin does not affect what happens whenever I spin the spinner, or roll a die, or pick a certain card out of a deck, right? Do we begin to understand how things could be mutually exclusive? Okay? No outcomes in common. For instance, it could be I'm spinning a spinner and trying to get, let's say that they're colored. All right, if you've ever played Twister, some of the things are blue, red, green, or yellow. Other things have arms or legs, right? Those things are mutually exclusive, okay, depending upon how the spinners are spun. To find the number of outcomes in an event that consists of mutually exclusive events, we would use the addition counting principle. Okay? The fundamental counting principle uses multiplication instead of addition. So suppose that k items are to be chosen if there are in sub 1 ways to choose the first two terms, in 2 ways to choose the second item, and so on. Then there's in your probability of the first times the probability of the second times the probability of the third times the probability, so on and so forth, till I get to whatever k represents, to choose all k items. So 2 events are independent if the probability of one event is not affected by whether or not the other event occurs. We use words like replaced to indicate that things are independent. So for instance, if I have a bag of colored marbles and I say, what is the probability that Diego is going to pull out, we've got 3 red, 4 blue, 5 green, something like that, and we could say, what is the probability of Diego pulling out a red marble, putting it back, and then Axel pulling out a red marble? Because he put it back, the probability doesn't change for Axel, right? The same number of red marbles are still in the bag, and the same number of total marbles are still in the bag, so those events are independent from one another, right? But if Diego pulls out that red marble and puts it in his pocket, now what happens to Axel depends upon what happened to, right? Because there may be one less red marble in the bag, right? And for sure there's one less marble in the bag no matter what it is that he got, right? So whatever Diego has is now affecting what Axel's going to get, right? Does that make sense? Okay. If we got Valentine's Day will be coming up in February, and you ever look at those mixed things of chocolates, right? And some of them are nasty and some of them are really good, right? You get one that's filled with caramel and then you get one that's filled with toothpaste, right? This is what it seems like. Okay, so and you don't always know what's in there, but right, if I pull one out and I get the caramel, now your odds of getting a caramel are less, right? Because I've got one. Okay, now if I get the toothpaste, your odds of getting caramel just went up, right? All right, so do we understand independent and dependent events? Okay. All right, so 2 events are dependent if the probability of one event is affected by whether or not the other event occurs. All right, let's try some of this out. Hopefully I can make some sense out of this and won't mess this up too terribly. All right, so you guys are going to look at this, then you're going to check the answer key to make sure I'm right, because I didn't pull my sheet of this out. Usually I've got a sheet where I've worked all this stuff out. So we want to find the number of outcomes when choosing a multiple of 8 or a multiple of 4 at random from the numbers 1 through 40. Okay, notice that it says or, right? So a multiple of 8 or a multiple of 4. So if we've got the numbers 1 through 40, and I'm not going to write them all out, but the first multiple of 4 is 4, right? Because 1 times 4 is 4, right? Right? And then 8 is a multiple of 4, right? And then 12, and then 16, and then 20, and then 24, and then 32, or wait, 28, right? 28, 32, 36, and 40, right? So find the number of outcomes when choosing a multiple of 8 or a multiple of 4 at random from the whole numbers 1 through 40. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? The number of outcomes should be what? What's the number of outcomes? What does it say at the bottom? It should be 10, right? There's 10 possible outcomes. Because it doesn't say multiple of 8 and 4, right? If it was 8 and 4, then I would have to go 8, 16, 24, 32, and 40. But it says or, so I could get a multiple of 4 or a multiple of 8. Wherever I have a multiple of 8, it's also a multiple of 4, right? So all that's affected. Does the answer key say 10? What does it say? It might say 15. It says 15. All right, here's the reason it says 15, which is I'm not thrilled about the answer, but it means that there are 10 options for 4 and there are 5 options for 8. We add those things up together, so we're using the addition counting principle, right? So we have 10 options for 4 plus 5 options for 8. We're getting 15 possible outcomes between those. Does that make sense? All right. There are 10 places to sit at a table. How many ways can 10 people be seated at the table? All right. This is a little different. All right. All right. So let's talk about the first person. Okay. We've got 10 people, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. How many different seats can the first person sit in? Nobody sat down yet. There's 10 different places he could sit. All right, but he sits down. Now how many places can the next person sit? 9, 8, 7, 6, 5, 4, 3, 2. Now the last guy, he's only got one place to sit. Do I add those up or do I multiply them? You multiply. All right, now there is a quicker way than taking 10 times 8, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that is because it's 10 times the descending order all the way down to 1. This is what we call 10 factorial, which we can do in our calculator, right? If you look, actually, let's see. Let me show you if I can remember this. All right, we'll pull this up. We got, here, let's clear this out. We have 10, then we're going to hit math, then we're going to go over to probability, and we're going to see a little exclamation mark. That means factorial. All right, so how many different ways can these 10 people sit down? It looks like a lot of different ways, right? So let's see, what is that? 3,628,800. Somebody check the answer key, is that right? Yeah, it's a lot of different ways those people could sit down. What we used was the, oh gosh, what did I just lost it. The fundamental counting principle. That's where we multiply the different places where these people could sit or how they could be picked. Okay? So we use fundamental counting principle for number 2. Do we understand that? Hopefully, a little bit. Okay? So, and we learned how to use factorial, which is something that comes into play in Algebra 3. All right, let's look at the number 3. There are 5 tiles in a bag labeled with the letters A, B, C, D, and E. The tiles are chosen at random from the bag without replacing them. Okay, that means what we're working with is dependent probability, right? Because we're not putting them back in the bag until all 5 have been removed. In how many different orders can the tiles be removed? Okay, so let's see. So how many letters do we have? 5. So we got 5, right? How many of them could be first? 5 of them could go first, right? So the question is, how many different orders could be chosen? Well, we're talking about probability, right? Then we'll notice we should be getting 4, 3, 2, 1, right? So what we'd be left with, I believe, unless I'm wrong, is 5 times 4 times 3 times 2 times 1, right? So we would be getting 5 factorial, 120. Okay, because 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120, 120 times 1 is 120. What's the answer at the bottom of the page? 120. So do we understand that? Okay. All right, thanks for the Spanish there. All right, when Richard went on vacation, he took a green shirt, a blue shirt. He also took a pair of navy shorts, a pair of beige shorts, a pair of white shorts, a pair of brown shorts. How many different shirts and shorts combinations could he wear? This is where we're actually going to use what you see as example number 1. All right, he took a green shirt and a blue shirt. So what we're going to do is we're going to take, here's his green shirt, here's his blue shirt, okay? He's got different shorts, right? We're not talking about socks and all that kind of stuff, or belts, those types of things. So how many different pairs of shorts does he have? 4? All right, he's got a pair of blue shorts, right? So he could wear a green shirt with blue shorts. He could wear a blue shirt with blue shorts, right? Does that make sense? Okay. He's got a pair of beige shorts. All right, we'll call them red, beige, beige. Okay. After that, he's got a pair of white shorts. I can't do white. We'll call them green. Okay. And then he's got a pair of brown shorts. Okay. So how many different shirts and shorts combinations could he wear? Comes down to 8, right? Do we see how that works? Okay. 1, 2, 3, 4, 5, 6, 7, 8. And that's how we break that down. All right. Let's see, this stuff, like I said, this all comes down to stuff that we did the other day. This question does the exact same thing that we just did with the shirts and shorts, except it's involving, wrapping paper and ribbons and all that kind of stuff, cards or tags. Okay, so wrapping paper, we've got striped or polka dotted, right? So striped, polka dots. Okay, so those are our main 2 options, right? Okay, then we could go bow or ribbon. So bow or ribbon, bow or ribbon. Okay, then we can do card or tag. 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 The final, how many different options we can come up with is our final row. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 different options. Does that make sense? Okay, so that we understand how to use a tree diagram to find out how many different things there are going to be to do there. Okay, I think you could probably also look at it as, you would have, say, you've got a 50-50 chance with either a striped or polka dot. You could probably do the addition counting principle there as well, but this tends to maybe make a little bit more visual sense than trying to figure out how to add those things. Okay, does that make sense? Yeah. Okay. All right. Do we feel like we've got this, or do we want to see anything else? Trying to look down here. I think that's pretty well it. All right, so I'm going to shut it off there and then answer any questions from your homework that you might have.